Hi students, welcome to this video session. My name is Samuel Chukwuemeka. In this video session, we shall discuss the topic of probability. Probability is an important subject in almost every field. Every field, in the social sciences, in business, in economics, in sciences, in banking and finance, in the mathematical sciences, in theater arts, in meteorology, every field you see probability. Now, have you used this word? Have you ever used this word, probably? Probably. Probably. Something, meaning likely, Hey, James, will you be coming to school tomorrow? And James will reply, probably yes. It's very likely, Then, if you listen to the National Public Radio, they might say there is 20% chance of rain, or there is 30% chance of snow. Chance, maybe 30% chance of snow. It means that the probability of having snow is 30%. That is what it means. These are just the common things we say about probability. There are so many things we do in this world that involves applications of probability. Okay? Even this concept of permutation and combination, choosing and selecting, is based on probability. So, in this video session, we shall discuss the general concepts, the vocabulary terms we will see here, and we can also explain what it means. Okay? So let's look at some vocabulary terms. We have a theoretical, classical probability. We have a empirical or experimental probability. Inequality range of probability. Inequality range of probability. We have expressing probability. What are the ways we can express it? Probabilities. English and math definitions. English and math definitions. Deterministic phenomena. We have a random phenomenon. We have an experiment. We have a outcome. We have a success. We have a failure. We have a sample space. We have an event space. We have events. In events, we have dependent events, independent events, mutually exclusive events, complementary events. So we shall talk about it later on in events. We have we didn't even mention history. We will talk about history of probability. That's the first thing we should have put. Okay, events. We have the laws of probability. Laws of probability. The addition law, the multiplication law, or the rule. Some textbooks say rules of probability. We have a conditional probability. Bayes theorem. Bayes theorem. We have applications of probability. And we can look at how we use probability in permutation and combination. Now, I did a video on permutation and combination. It is under discrete math. Okay, permutation and combination. I did videos on them, and it is under discrete math. It is under probability here. Now, this video will be on my website. I am going to put it under your class, finite math, and I will also put it under probability. Okay, so when you go to my website, as usual, samuelchukwuemeka.com, you click on my picture to enter the site, you click on mathematics, you click on finite math, and you will see this video in your under finite math. I will also put the video under probability. So I will also put it there. Now, if you go and click also probability, they mentioned that I did videos on permutation and combination. It falls under here. So you can view those videos as well. They didn't mention it a lot in your book, but if you want to have a good idea about it, you view the videos as well. Okay, so probability is a very broad topic. It is broad. I mean, it's a lot. It's a lot of things we will do. We probably will not follow this in order. We are going to explain it. Let's look at a case of coins, case of dice. Look at the three diagrams. Look at three diagrams. And Punnett square. Punnett squares. We are going to, it's a lot, it's so much, you know. We will, as we go on, we might add to these terms. As we go on, we might add to these terms. And we may not follow it in order as it is written. I will explain it, and I will explain it, and then you can write, okay? Where I will need to solve is the case of coins, dice, tree diagrams, and Punnett squares. And sometimes when I need to write formulas, yeah, but I am going to explain it, and then you can write it in your notebook, okay? This might not be all. It is not exhaustive. As we go on, if it's something that you need to know, I'll put it, and we can discuss it. This is just the part one of this video. There are some other videos that will be coming under this probability. Okay, so let's look at this now. Let's say you go to Walmart or Walgreens or JCPenney or Target, you know, or Kmart, you name it. If you have that, maybe you want to buy I like buying oranges. Oranges is good. So let's say that, or banana, I also like buying banana also. So let's say that a pound of oranges is maybe $2, right? Assuming a pound is $2. So $2 per pound. They write it as this, $2 per pound. Okay, so if I buy a bunch of them and I go to the checkout register and it is, if it is $6, before I go to the checkout register anyway, before I go to the checkout register, I will weigh it. A pound is $2. So if I weigh it on the scale, on the weighing scale, if it is 6 pounds, that means I already know what I will pay in the checkout. How much will I pay? $12. Okay? So I already know what I will pay. So in that case, it is a deterministic phenomenon. Okay? Because you already know what the outcome will be in advance. Okay? You can predict what the outcome will be. Now, outcome means results. Outcome means result. Now, you can predict what the outcome will be, how much you will pay in advance, because you have this information already, and it is $2 per pound. So if you have 6 pounds, you will know that you are going to pay $12, then including tax. Okay. Now, that is a case of deterministic phenomenon. A phenomenon whereby you can predict the outcome based on the information you have. That is what we call deterministic phenomenon. Now, not every phenomenon is deterministic. Okay? What if I come now and, I don't know, when I taught this topic in middle school, I use dice. Yeah, I usually bring dice, I usually bring dice. Now, if I assume I have a dice means 2. If it's 2, it's dice. If it's 1, it is die, a fair die. We call it a fair die. A fair die. Or let me say a fair coin. A fair coin. Assuming I have a fair coin. Now, this is not magic, okay? If I have a fair coin now, and I toss it one time, if I toss it one time, will you know, am I going to know what will be the outcome already? I mean, if I toss it one time, I don't know whether it's going to fall on the head or whether it will fall on the tail. I do not know, and you do not know either. It is just a toss. You close your eyes, you toss it, okay? Or whereby you have this lottery, when you do, when you take state lottery, although Alabama does not do state lottery. Alabama is so, well, anyway. So let's say you go and you buy lottery, or maybe you go to all these, fundraising lottery. They give you a paper lottery, all this fundraising, and they call somebody, hey, close your eyes, and they shuffle all the tickets, and somebody just closes his eye and dips it, picks it up. He doesn't know who will win it. They don't know. So in that case of a phenomenon whereby you cannot predict the outcome, we call it a random phenomenon. Okay? Back to the store. Take it back to Walmart. Okay? If the manager, let's say, hey, the manager, maybe he, from the way things are going, maybe he sees that, okay, if he has 10 bags, if he brings maybe 10 bags of oranges, it finishes that day, So maybe the next day he brings 11 bags and maybe it finished. Next day he probably bring next day he probably brought 11 bags, and maybe only 2 bags were sold. The 9 bags were left. Okay, so it is something that is not predictable. I mean, it is not always predictable. Okay, even the 30% chance of snow that you hear in the public radio, the meteorologist will say there is 30% chance of snow. Or even if he says there is 80% or 90% chance of snow, which means it's a high probability, very likely that it will snow. Tomorrow might come and it will not snow. Have you not witnessed it before? So it is a random phenomenon. You cannot predict the outcome beforehand. Okay, you cannot predict the outcome beforehand. So a random phenomenon is a phenomenon whereby the results cannot be predicted in advance. Okay, now when we observe or measure a random phenomenon, it is called an experiment. An experiment is observation or measurement of a random phenomenon, because you will have to observe, okay, like the manager will have to observe. The first day, 10 bags were sold. Second day, 11 bags, he brought 11 bags, it was sold. So he's kind of performing an experiment, noticing, observing how many bags are sold per day, so that he can predict what might come the third day. Bring it back now, forecasting, what we know as forecasting. You know, maybe every 25 years, earthquake will occur in this region. You've been observing it, maybe every 25 years. Now, 25, it might be the 50th year, or it might, okay, maybe it's 25th year, earthquake happened, 50th year, earthquake happened, 75th year, earthquake happened, maybe the 100th year, earthquake did not happen in the 100th year. It didn't happen in the 101st, it didn't happen in the 102nd, it didn't happen in the 104th, it might happen in the 105th, to tell you still that that is a randomness. But you have been observing it. You've been observing that every 25 years it occurs. So you might now say you are not very, very certain, but there is a high probability that it will occur. So in probability, we are just using like it is a measure of something that will likely happen. Yeah, it is not for certain that it must happen. It is just a measure of the certainty of an event, that the event will happen. That's why you say high probability, likely. So that is random phenomenon. There are so many examples. And then observation of a random phenomenon is called an experiment. Okay, now the possible outcomes, the results of an experiment is what we call an outcome. Okay, the possible results of an experiment is what we call an outcome. Now, when we have a favorable outcome from an experiment, let's say you are tossing, you're doing a game, now let's deviate a bit. Why are we learning this topic? How did it even originate? And this is what I should have taught you first time. Okay? This probability came from gambling, games, games, lotteries, gambling. That is how this idea of probability originated. Yeah, this topic we are learning now originated from the idea of gambling. Cheating in gambling. Okay, Cardano, Girolamo Cardano, he used to cheat. He wrote papers on how you can cheat during gambling. Okay, now there are some people who did some significant work in this topic of probability. We have the Italian guy is Italian mathematician Girolamo Cardano. Yeah, besides probability, he did a lot of work in mathematics. But he's a cheater, He wrote a book on how you can cheat using in games of chance, gambling. Girolamo Cardano. Okay? That's an Italian Now we have some Russian folks that are that did some work here. We have a Chebyshev theorem, Chebyshev. We have a Markov. We have a Kolmogorov. Then we have some French folks. We have some French guys that did some work here. Some French folks that did some work here. We have a Fermat, Pierre. I don't know what I'm pronouncing it right. Pierre de Fermat. And later on in math, you'll hear about Fermat's theorem. Then you have this another guy is Laplace. Let me not break his name, so let me just write it here. Pierre Simon de Laplace. You talk about Laplace transforms. Okay? You also have this guy, Blaise Pascal. Blaise Pascal is a French scientist. Pascal's triangle. Pascal's triangle helps you in even binomial theorem, binomial expansion formula. Okay, it helps you. In fact, it was actually written from Pascal triangle. You know, it's nice. Who else now? We have Bayes. Bayes is another person. Bayes theorem of unconditional probability. Yeah, I don't know from what country he's from. Yeah, but these are some guys that we can give accreditation that at least did some work in probability. So this is a game of chance, gambling, lotteries. They are all the same. You know, anything that you cannot predict the result in advance. Okay, you're taking some risk. You know, you don't know exactly what the outcome will be. It's about probability. Okay, it's a game of chance. Now, where was I now? So, success is what we call a favorable outcome. Let's say you toss a coin, a fair coin, and you want the head. You want it to land on the head, right? If it lands on the head, that is success. If that is a favorable outcome, a favorable result. Okay. If it does not land on the head, then it is a failure. So, favorable outcomes of an experiment is what we call success. Unfavorable outcomes of an experiment is what we call failure. Okay, this is a positive outcome, this is a negative outcome. Now, sample space. Sample space is a set of all possible outcomes, all the possible results we can get from an experiment is what we know as sample space. And we're going to deal a lot on this. It's very important that you understand this concept. It's very, very important. It is very, very important that you understand this concept of sample space. Very important. So we will spend some time on it in this video. And also event space. So, like I said, sample space is a set of all the possible outcomes, all the possible results you can get, both the favorable ones and the unfavorable ones. That gives us the sample space. Now, event space is sometimes we are not interested in unfavorable outcomes. Sometimes we're not interested in failures. We are just interested in some collection of outcomes, the positive outcomes, the successes. Okay? So we are interested in just how many successes we want. We are not interested in the failure. So that collection of some outcomes, which is also a subset of the sample space, okay, I'm saying subset, set theory. I hope you have an idea of sets. Okay. Now that collection of outcomes of a random experiment or random phenomenon, okay, which is also a subset of the sample space, is what we call an event space. Okay, that's what we call an event space. So we are going to pay a lot of attention to these folks here. Events. We are going to look at events in another video. Okay, we have dependent events, independent events, mutually exclusive events, and then complementary events. Okay. The laws of probability, we will look at that in another video. Addition law, multiplication law. Conditional probability, we will look at that in another video, and also applications. Now, we are in this case, with this video, we shall look at coins, dice, tree diagrams, and Punnett squares. We shall look at it. Okay. Now, back to here, theoretical or classical probability. Let me explain this. There are some, under the random phenomenon also, there are some cases whereby every outcome has an equal likelihood of occurring. Now, let me take you back. I say that success is the favorable outcomes of an experiment. So that means when we observe a success, that means an event has occurred. Okay, when we observe success, an event has occurred. Now, some of those events, in some events, okay, in some cases, some outcomes have equal likelihood of occurring. Okay, they have equal probability. When we say, if I say likelihood, I'm meaning probability. Okay. Now, in some events, the outcomes in some events, all the outcomes have an equal likelihood of occurring. Just like when you toss a fair coin, the probability of the head occurring is the same thing as the probability of the tail occurring. No one has more advantage than the other. When you toss the coin, it could land on the head or on the tail, assuming it doesn't land on the side, which is very unlikely, okay? Because it will land on the flat surface. So it's gonna land on the head or on the tail. If you just toss it, both of them have an equal likelihood of occurring. That case, the probability of such events is what we call the theoretical or classical probability. Because we can calculate the probability just by mathematics, with the formula by mathematics. Sometimes we call it mathematical probability. Okay, this is the probability in which this is the probability of events in which each outcome of the event has an equal likelihood of occurring. Each outcome of the event has an equal likelihood of occurring. Okay, or of occurrence, you can say of occurrence. Occurrence, yeah, has an equal likelihood of occurrence, or equal probability. Each outcome of the event has an equal probability to occur. So, in that case, we say that it is theoretical or classical probability. We don't need an experiment to do theoretical or classical probability. Experiment is not needed because the outcomes have equal probabilities of occurring. Okay? And of course, the sample space is finite. We're not talking of infinite sample space. Here, all the problems we will do in the topic of probability shall be for finite sample space. Sample space that is finite, that you can count. Okay? Now, but sometimes it might, all the outcomes of the event, all the elements of the event, all the outcomes of the event might not have the equal probability of occurring. In that case, you will need an experiment. Now, that is experimental probability. You need an experiment, several experiments in order to determine the probability. Okay, we are going to look at this inequality range of probability. Then expressing probability. Probability can be expressed as a fraction, or a decimal, or a percentage. Let's look at some. Let's look at some. The probability of an event. The probability of an event. Probability of an event be P. Okay, let the probability of an event be P. P of E. Yeah, let the probability of an event be P of E. So, inequality range of probability. What does this mean? We have that 0 is less than or equal to probability of an event is less than or equal to 1. This is known as the inequality range of probability. What does this tell you? This tells you that the probability of an event is between 0 and 1. It cannot be less than 0, it's not going to be negative, and it cannot be more than 1. Now, the probability of an impossible event, the probability of an impossible event. What is an impossible event? This is an event that cannot occur, an event that can never occur, is 0. Okay? The probability of an impossible event is 0. The probability of a sure event. A sure event. I don't know whether I'm using the correct grammar, but let me say of an event that must occur. Probability of an event that must occur is equal to 1. So you see, 0 and 1 are the two extremes of probability of an event. Probability of an event lies between 0 and 1. 0 being the probability of an impossible event, and then 1 being the probability of an event that must occur. Okay? Now, probability of an impossible event. What is an impossible event? Probability that men will get pregnant. You know there's no way men will get pregnant. It's not going to happen. So, the probability is 0. Probability of a man having kids is 0. The probability we believe that Jesus Christ will come again to judge all mankind. The probability is 1 of an event that must happen. Is 1. Okay, now, any probability lies between 0 and 1. Remember, whatever problem you're solving, whatever probability of an event that you are calculating, if it is less than 0, you are wrong. Just know that it's wrong. Okay? You cannot have a negative. And you cannot have 1.1. You cannot have 1 whole number 3 over 4. You cannot have it. You cannot. Anything you're calculating in probability will be between 0 and 1. And the probability of an event, P of E, can be expressed, as a fraction. Okay, of course, in this case, you will always have a proper fraction. You always have you will have a proper fraction. Usually, it is between 0 and 1. Okay, it's most of the calculations we will do is, is going to be between 0 and 1. Now, this inequality sign means that 0 and 1 are included. Yeah, and remember 0 and 1 are the two extremes, that's why. So it can be expressed as a fraction or as a decimal. It can be expressed as a decimal or it can be expressed as a percentage. So if I say 20% chance of rain, 20% chance of rain, it means 20 out of 100. That's what it means. 20% chance of rain. It means 20 out of 100, which is what? 0.2. Or, which is 1 over 5. Okay? It can be 20%, or it can be decimal, or it can be fraction. Just know that. Probability of an event. Okay, now let's go ahead and define these probabilities, theoretical probability and empirical probability. Let's go ahead and define them. For instance, the theoretical probability, let's start with that. Classical or theoretical? Theoretical probability. Let's give the English definition and the math definition. Like I said, this is the probability in which all the outcomes of the event have equal likelihood of occurring. Okay? All the outcomes of the event have equal likelihood of occurring. So in this case, we have that the probability of the event is the number of required outcomes. You can say required or favorable outcomes. That is successes. Number of required outcomes all over number of possible outcomes. Okay? So this means that probability of the event is equal to the cardinality of the event space. Like this is, I'm using some set terms. Yeah, it will be good if you have an idea of sets. Okay, I have some resources on that on my website. Cardinality of the event space all over cardinality of the sample space. So this is cardinality. Cardinality. Cardinality is the number of elements in the set. Cardinality of the event space all over the cardinality of the sample space. Cardinality of the sample space. Cardinality just means number of, okay? Cardinality of the sample space. Empirical or experimental probability, you have that if it was empirical or experimental probability. In this case, you have to do experiments. It is a situation whereby all the outcomes of the event do not have equal probability of occurrence or equal likelihood of occurring. In this case, the probability of the event is, now in this case you have to do experiments repeatedly. So the probability of the events will be the number of times the event occurred. The event occurred all over number of times the experiment was performed. There is something I remember now that I should have put in the vocabulary, and that is the law of large numbers. Law of large numbers. But we will do that in next video. We'll do it in next video, okay? A number of times the experiment was performed. Okay, that is the for the empirical or experimental probability. Example 1. List the sample space and give the cardinality of the sample space for these events. Okay, so let's begin from here. Now, why am I doing this? In any probability question that you will be asked, okay, or that you want to solve, you need to know the sample space. You remember the probability of an event is the cardinality of the event space divided by the cardinality of the sample space. Event 1, first event, let's say toss of a fair coin. When you toss a fair coin, now, of course, our sample space, let the sample space, anytime you see the sample space, we usually denote it as S. S, that is what it is. Okay? So, if we say toss of a fair coin, the sample space will be the set of, please, this is not parenthesis. It is not. I think this is I'm not sure whether it's braces, okay, but this is the way you write it. This is sets. Sets, you do your hand like this, as if you're doing an integral sign. An integral sign, you do it like this. And then from here, you now do like this. You can practice it, it's not difficult. Okay? And if you want to close the set, you do your hand like this. Do it like that. And then from here, you now do it like this. No, now do it like this. Yeah. If those are braces, yeah. So that's your set notation. Set notation. Okay, so if you toss a fair coin, you can either have the head or the tail. Okay? So the cardinality of the sample space will be 2. Cardinality of the sample space will be 2. Now, what if I ask you now, find the probability of having a head? Find the probability of having a head in a single toss. In a single toss of a fair coin. What's the probability of having a head? In this case, if I ask you what is the probability of obtaining a head. So remember that probability, remember what probability is. Probability of an event is the number of the event space, cardinality of the event space, all over cardinality of the sample space. So you ask yourself, what is the cardinality of the event space? How many heads do you get here when you toss a coin one time? You get only one head, right? So this means that NH is 1, right? So you get only one head, and that means that, this means that probability of having a head will be cardinality of the event all over cardinality of the sample space. Okay? So which is now 1 over 2. 1 over 2, half, 1/2, or 0.5, or 50%. The same thing, what is the probability of having a tail? A tail. You ask yourself, how many tails do you have when you toss a coin one time? How many tails do you have? You have only one tail, right? So, if you have only one tail, then what is the probability of having a tail? It is now 1 over 2. Toss of 2 fair coins is the same thing as a single toss of two fair coins, or you can say two tosses of a fair coin, is the same thing. Yeah, you can either write it as toss of two fair coins or two tosses of a coin. It's the same thing. Okay, so what would this be now? You can now do this in either tree diagram or Punnett square. That brings us to tree diagrams or Punnett squares. Okay, usually I prefer Punnett squares, but I'm going to teach you how to do it with both of them in this case. Now, all these are theoretical or classical probability, all of this. Because here, the head has an equal probability of occurring as the tail. So here, if we are using tree diagram, okay, you can have it this way. You have a first coin, head and tail. This is your first coin or first toss. And then for the second coin, here I call this first coin here, first coin. Then for the second coin, you have, for each head, you have head and tail. And then for the tail, you have head and tail. Head and tail. Okay, this is the second coin. Or maybe the second toss. Okay, a single toss of two fair coins is the same thing as two tosses of one coin. Yeah, that's the same thing. Okay, so if we do the tree diagram, you can, it could be a head on the first coin and a head on the second coin to give you head. It could be a head on the first coin and a tail on the second coin to give you head, tail. It could be a tail on the first coin and a head on the second coin to give you tail, head. Then it could be a tail on the first coin and a tail on the second coin to give you tail, tail. So what is the cardinality here? What is your sample space, and then what is the cardinality? Let's list it. So the sample space. Will be set of head, tail, tail, head, and then tail, tail. The sample space will be a set of head, tail, head, and tail, tail. And what's the cardinality of the sample space? It is 4. Cardinality of sample space is 4. Cardinality is the number of elements. 1, 2, 3, 4. Number of elements in the set. Okay? Now this is with tree diagram. Let's do it with Punnett square. If we do it with Punnett square, and how did this Punnett square come about? When you do in your biology, genetics, when you did the study of genetics, law of segregation of genes, Gregor Mendel's law, Mendelian laws of genetics. The first one is law of segregation of genes, and the second one is the law of independent assortment of genes. You know, when he planted the red and white peas, what will you have in the first filio generation? Okay, that a Punnett square could be used to explain that, and we still do the application here in mathematics. In this case, you have it this way. You have the first coin here. Now, in my Punnett square, there's the way I draw my own Punnett square. I kind of draw it my own way. I try to draw two lines to demarcate it. And here is going to be my head and the tail. And this is going to be my first coin. Okay? And I have here head and tail. and this is going to be my second coin. You know, I usually put 2 lines here to differentiate the first coin and the second coin. So it could be head on the first, head on the second, head on the first, head on the first, tail on the second, head, tail, tail on the first, head on the second, tail, head, and then tail on the first, tail on the second, tail, tail. When you toss it, those are the possibilities you can get. You can either get head, head, you know, or head, tail, or tail, head, or tail, tail. Okay, now this with the Punnett square, and this starts with the 3 diagrams. Okay, now what if I ask you this? What if I ask you this? What's the probability of getting, let me kind of do some questions here. What if I ask you this? What is the probability of getting 2 heads? What's the probability of getting 2 heads? So this will be probability of head, head, right? So which is cardinality of head, head. How many head do we have? All over cardinality of the sample space. So how many head do we have? 1 over 4, or 25%. That's probability of getting 2 heads. Okay? What's the probability of getting a head and a tail? A head and a tail. Okay? A head and a tail could be head, tail, or tail, head. When we do lots of probability, you will see that why I said or. Head, tail, or tail, head. Yeah, but we're not going to do lots of probability in this video. So a head and a tail could be head, tail, or tail, head, and that is what? 2 out of 4, which is 1 over 2. And what's the probability of getting 2 tails? 2 tails. It will be what? 1 out of 4, because you only have 1 chance. Okay, 1 out of 4, which is 0.25 or 25%. Now, what if I ask you this? What's the probability of getting at least a head? At least a head means at least. Let me give you this now. If I say at least 5, okay, it means 5 or more. Okay? It means greater than or equal to 5. Now, this is what it means if I say at least 5. If I say at most 5, it means 5 or less. So that is less than or equal to 5. Okay? If I say exactly 5, it means equal to 5. One head is inclusive. Remember this equal sign. Okay, it's inclusive. So it could be 1, 2, or 3. It could be head, head, or head, tail, or tail, head. And I will give you 3 over 4. Excuse me. Okay? If I say probability of getting no tail, is the same thing as what? Getting no tail. No tail at all means what? 1 over 4. 1 over 4. If I say probability of getting no head, it will be only tail, which is 1 over 4. Right? If I say probability of getting at least a tail, it will be what? 3 over 4. Now, do you know why I did this? Can you tell me something here? Probability of getting at least a head means 1 minus probability of getting no tail. Probability of getting at least a tail means 1 minus probability of getting no head. Given 3 means toss of 3 fair coins or 3 tosses of a fair coin. 3 tosses of a fair coin is the same thing. Whether you say toss of 3 fair coins or 3 tosses of a fair coin. You know, tree diagrams is not always drawn like that. You can draw it any way you want. You know, you can draw it like a tree that rises. You can draw it like a tree that falls. You can draw it like a tree that moves like this. Or you can draw it like a tree that moves like this. So in this case, let's try something else, right? And I say first toss. First toss, I have the head and the tail. First toss, I have the head and the tail. Second toss. For this head, I have head and tail. For this tail, I have head and tail. Third toss. Okay, just like you have, like I say first coin, second coin, third coin. It doesn't matter. Okay? Third toss. For the head, I have the head and the tail. For this tail, I have the head and the tail. For the head here, I have the head and tail. For this tail, I have the head and tail. Okay, let's look at it like a tree. So the sample space will be cardinality of, I have head, head. It could be head on the first toss, head on the second toss, head on the third toss, head, head, head. Then it could be head on the first, head on the second, tail on the third, head, head, tail. It could be head on the first, tail on the second, head on the third, head, tail, head. It could be head on the first, tail on the second, tail on the third, head, tail, tail. Right? Let's leave this as the first outcome. Then it could be tail on the first, head on the second, head on the third, tail, head, head. Then it could be tail on the first, head on the second, tail on the third, tail, head, tail. It could be tail on the first, tail on the second, head on the third, tail, tail, head. It could be tail on the first, tail on the second, tail on the third, tail, tail, tail. So the cardinality of the sample space is what? 8. 1, 2, 3, 4, 5, 6, 7, 8. You can get 8 outcomes when you toss a coin 3 times, or when you toss 3 coins 1 time. Okay? Here, you toss 3 coins 1 time, or you toss a coin 3 times. You toss a coin 3 times. These are the outcomes you can get. What if we do it with Punnett square? What are we going to get when we do it with Punnett square? We have our 2 coins. What's the outcome of the 2 coins? And then I usually draw mine like this. You know, with Punnett square, it's 2 coins and 1 coin. Okay? So I have my 1 coin here, which could be head or tail. And with the 2 coins, you can have head, 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 tail, tail, head, and then tail, tail. So it could be head, 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 head on the first, head on the second, head on the third, head, head, head. It could be head, 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 tail. It could be head, tail, head. It could be head, tail, tail. It could be tail, head, head. It could be tail, head, tail. It could be tail, tail, head. It could be tail, tail, tail. Let me ask you this now. If it's 4 coins, what do you think the cardinality of the sample space will be? For 4 coins, what do you think the cardinality of the sample space will be? You know, now for one coin, the cardinality of the sample space was what? 2. 2 raised to power 1, which is what? 2. For 2 coins, The cardinality of the sample space was what? 2 raised to power 2, which is what? 4. For 3 coins, the cardinality of the sample space is what? 2 raised to power 3, which is what? 8. So for 4 coins now, what do you think it will be? What do you think the cardinality of the sample space will be? It will be 2 raised to power 4, which is what? 16. Head, 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 head. Head, 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 tail. Head, head, tail, tail. Yeah, you list it, it should be up to 16 times. Head, 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 head. Now for 4 coins, use 2 coins here and 2 coins here. So you have head, 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 head. Head, 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 tail. Head, head, tail, head. Head, head, tail, tail. Okay? Then head, tail, head, head. Head, tail, head, tail. Head, tail, tail, head. Head, tail, tail, tail. Tail, head, head, head. Tail, head, tail, tail. Tail, head, tail, head. Tail, head, tail, tail. And then tail, tail, head, head. Tail, tail, head, tail. Tail, 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 head. And tail, 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 tail. Okay, that should be 16. I want you to try it on your own. Okay, try it on your own. And then for the 3 diagrams, remember you have to draw another 4th coin here, or 4th toss. For each head you have head and tail. For the tail you have head and tail. Head and tail. For each head you have head and tail. And then you count it. It should be 16. Try it on your own. If you have question, then you ask me, and I can do it, the 4 coins for you. Now, I wanted to teach you this formula. Okay. Now, guys, we now have a formula here. Okay. We have that the cardinality of the sample space is the number of faces raised to power number of tosses. You probably won't see this formula in your textbook, but just take note of it. Yeah, I mean, most is not, I've not seen it in textbook, I have to. I made it up, you know, I made it up through through solving this kind of questions. Now when we go to dice, it's also in dice. It may be in some textbook, but it's something that I made up, you know. So number of faces raised to power number of tosses. Yeah. For a coin you have 2 faces, so that's why 2. 2 is the base. And then the exponent, the base is number of faces and the exponent is number of tosses. Yeah. It doesn't work out, this is not for every, this is for unique case of coins and dice. Yeah. My research interest is statistics. I look into probability sometimes, so. Okay. That's for coins. Let's stop here, and next video we shall do dice. We shall do dice. In dice we shall only stop at 2 dice. Okay. Finish up this case for 4 coins tossed 1 time, or a coin tossed 4 times. It will give you the same sample space. Just find the sample space. And then when we come next time, we will do more calculations on finding the probability. And then we'll do dice. We look at sample space for 1 die. A die has 6 faces. So we toss it 1 time. The sample space will be 6. We toss it 2 times. The sample space will be 6 raised to power 2, which is 36. Yeah. We toss it 3 times. It will be 216. But anyway, we'll stop at 2 times. Yeah. Now, go ahead and do the 4 coins, you know, and if you have questions, just let me know. And we will see the next part 2. Okay? Thank you so much, students, for listening. And you have a great day.